Hey you, it's me again. Still not 100% about this whole Quideo thing, but here goes nothing. Unit numero dos is up for today. For the basic problem, we had to focus on the usage of regression lines to predict values. The problem was given with Professor Moore's recorded 2,000 yard swim along with his pulse rate after swimming that 2,000 yards, with the task of not only confirming that the linear model was appropriate for the data, but predicting values on either side of the data. We also had to explain why there were two separate regression lines that we had to use for the predictions of the data. To confirm that a linear model is the best representation of this data, we had to first find the regression equation of the scatter plot. To find this, I ended up calculating this with the linear regression that we use in stats to calculate the a and b values of the equation. We ended up finding that the equation is y equals 479.934 minus 9.6949 times x. This then helps to determine the regression graph, which is an indicator of the linear form of the data. So when you look at the graph here, the regression graph, it ends up telling you that this is a very, very linear graph, and so this regression would be a good model of the data. Next, we were tasked with predicting the pulse rate of Professor Moore after swimming from his swimming time that we were given. This would be calculated from the regression equation that we found in the last slide. So the equation would be, again, y equals 479.9341 minus 9.949 times x. Plugging this in the given swim time of 34.30 minutes, we were presented with a predicted pulse rate of 146 beats per minute. This value is extremely far away from the actual value that we were told of 152 beats per minute. After predicting the pulse rate from the swimming time, we were also tasked with working backwards from the pulse rate to get the swim time. This would be calculated with a new regression equation where the pulse rate is used as the x value instead of the swim time, as in the last equation. Therefore, the equation for this is y equals 43.0973 minus 0.0574 times x. Plugging in the given value of 152 beats per second, we are presented with a predicted swimming time of 34.37 minutes. This is quite accurate compared to the actual value of 34.05 minutes that we were given in the data. Now, in the last slide, we found a brand new regression line to calculate the predicted swimming time. We had to do this because the two sets of data have entirely different residuals. They need to be calculated separately to account for the difference in residuals. For the advanced problem, we also had to focus on the usage of regression lines to predict values on either side of the equation. The problem was given with the size of flash drives and their respective costs, with the task of finding the regression equation without a calculator. We also had to predict the slope and the y-intercept of the data, as well as predicting the price of a specific size of flash drive, and determining if the price found by Shaheen is a good price compared to the predicted value given from the equation. In the data, we are given both the y-intercept and the slope in the form of coefficients. The constant coefficient in the problem is the y-intercept, and the other value would always be the slope. So the y-intercept is 18.617, and the slope is 103.929, making the equation y equals 18.617 plus 103.929 times x. The slope of the data is the change in the connection between the capacity of the flash drive and the price of the flash drive. The y-intercept of the data is the price of the flash drive that has a size of 0 terabytes. When you're predicting the y value of a dataset, you must use the regression equation for the data, plugging in the x that you want to find the y for. In this case, we're finding the price of a 3.0 terabyte flash drive. Plugging this value into the equation found on the previous slide gives you a price of $330.40, with the $300 flash drive that Shaheen found being our actual value. It's a steal compared to the predicted flash drive price that we just calculated. Being that it's $30 below the predicted price, it's a fantastic buy, and Shaheen should really get that nice flash drive. That would be a really good investment for me. For the AP problem, we also had to focus on the usage of regression lines to compare values on one side and determine the proportion of the variation. The problem was given with the data output from a computer that tracked both the wind speed on the day and tracked the electricity generated by the windmill, with the task of determining the equation of the least squares regression line with its variables and comparing the electricity production on 2 separate days with different wind speeds. We also had to define the proportion of energy production that is determined by its relationship with wind velocity. Just like the advanced problem, the y-intercept and the slope are given to us in the data as coefficients. Therefore, the y-intercept of the data is 0.137 and the slope is 0.24. This created an equation of y equals 0.137 plus 0.24 times x. To compare the electricity production between the 25 mile per hour day and the 15 mile per hour day, the values 25 and 15 have to be plugged into the regression equation that was found on the previous slide. These calculated values for the 25 mile per hour day is 6.317 amperes and the 15 mile per hour day is 3.737 amperes. This creates a difference of 2.4 amperes. To find the proportion of the variation in electricity production that is explained by its relationship with wind velocity, we must first find r squared. This is given to us in the computer output, so we can instantly use this to our advantage. Out of this, r squared here is 0.873 of the electricity production. So 0.873 of the electricity production is explained by the wind velocity on that day. And I guess with that, we wrap up our second Quideo. I just hope you get a lot more confident about this. Be you soon.